Hello everyone, this is Boyd Wilson, and today we're going to spend a little time going behind the scenes of CloudyCluster on Google Cloud Platform. One of the main goals of CloudyCluster is to provide the familiar HPC experience we are used to, but also provide all the flexibility and scalability of Google Cloud. Today we'll be looking at what happens when you run the create SA script from the Cloud Shell, launch a control instance from the GCP Marketplace, create an HPC environment from within CloudyCluster, and launch HPC jobs through CCQ. To start, there needs to be a GCP project that has the prerequisite items configured, such as enabling the APIs and also setting up Firebase as the cloud database. In the GCP project, there will be a default VPC and a default subnet automatically set up for you. And when the create SA script runs, it'll actually create a control service account. The service account has the minimum required permissions for CloudyCluster to operate, and the philosophy of least required privileges is used throughout CloudyCluster. Now that the base security is set up, next the control instance will be launched from the GCP Marketplace. After the control instance is launched, it self-configures, and it creates a Firebase table to hold all the CloudyCluster metadata, fetches a DNS name, and once that propagates, it actually receives a Let's Encrypt certificate, so all browser communications are encrypted. Once all this happens, the primary user can log in and do the initial setup through a web browser that has a fully trusted site and full TLS encryption. After the primary user finishes setting themselves up, they can actually go ahead and add additional collaborators as needed. And these users are automatically provisioned to the various HPC nodes as they come up. The next step is the creation of the HPC environment through the CloudyCluster UI. The first thing that happens when the HPC environment is launched is the creation of various SAs. Each of these SAs has the least privileges required for the type of instance it is associated with. The next thing that happens is an HPC virtual private cloud is created, or VPC. There are three sets of subnets created: the public subnet, the storage subnet, and the private subnet. And they're pretty self-explanatory. Following which, NAT is created so all of the items in this HPC VPC can have outbound internet access. The login instance is then created, and it also gets a domain name and a Let's Encrypt certificate. Following which, the parallel file system instances are created. And these are created based on the configuration that you selected based on size of instances, which will affect network performance, and the amount of storage needed, which will also affect performance on the storage backend. Following this, a GCS bucket is created, and all of the instances within the HPC VPC have access to this GCS bucket. And Stackdriver is also configured for the instances to ease logging across all the instances. Once the other items are ready, the selected scheduler, Torque or Slurm, will be launched and configured to run with CCQ, a metascheduler that comes with CloudyCluster that allows researchers to configure their Slurm or Torque jobs to run with the size and capabilities of instances needed for their workloads. These jobs can easily be configured to run on-prem and in the cloud without change. The jobs will also automatically set labels for the user so that the researcher's usage can be tracked in the GCP billing system. The job can also contain identifiers that can be used to link projects across researchers for budget allocation and reconciliation. Now, research users can securely connect, configure, and run their HPC jobs through Open On Demand or through SSH, which they can optionally configure for multi-factor authentication as required. When a researcher launches a job that needs, say, 60 vCPUs for an MPI job, they'll want to use the C2 instance type. When C2 instance types are launched, CCQ will launch the instances using placement policies, so the instances can reside close together, providing a low latency connection between them. Here's a researcher-launched job that is configured for GPUs, and here is a high throughput job that is configured for preemptible instances, so they can save up to 80% of the cost, with the understanding that a node in a job may get preempted. Now, when the CCQ jobs are completed, CCQ will make sure that there are not any other jobs in the queue that need that instance type, and then it'll delete the instances. So you no longer build or see any billing for those. So here's another job that finishes, and here's the final GPU job that finishes. Now that all the jobs for the session have been run, the primary user can stop the environment, which would stop all the instances and reduce the spend to just the storage costs. When additional jobs need to be run in the future, the primary user can come back and start the HPC environment again from the CloudyCluster UI, and everything will be ready to go in just a few minutes. I hope this helps show some of the details that happen behind the scenes with CloudyCluster on the Google Cloud Platform. Thank you and enjoy.